In this video, we will discuss the moment of inertia for a rod of rectangular cross-section area and a plate. So, yesterday we discussed the moment of inertia for a rod for about two axes. One axis which was passing through the center and perpendicular to the length, and another axis which was passing through one end or one corner and perpendicular to the length. But today we will take the rod of rectangular cross-section area or a plate. So I would like to make you understand first what is the rod of rectangular cross-section area. Here I have this book, and this book, when you look from here, it has a length and a breadth, but thickness in comparison to length and breadth is very small. So we don't consider the thickness of this book. When we consider the length and breadth, both are considerable, so we cannot negligible the breadth of this. But in case of rod, all the length and breadth are negligible in case of length comparison to the length. So this book or any plate of a rectangular cross-sectional area is it comes in this case of rod of the rectangular cross-section area or a plate. So I wrote down the both of the things because in the examination or in the books, both of the things are given in the different books. So today we will take determine the moment of inertia for a rod of rectangular cross-section area or for a plate. The plate look like this, in which we have one length and one breadth. When we draw it, it will be here. This is the length. This is the length of the plate. This is the breadth of the plate. We assume that mass of plate is capital M. So first, we will determine the moment of inertia from about an axis passing through here, passing through the center and perpendicular to the length. So when we consider it, in the case of breadth, the half portion is here and half portion is here. So in first case, the moment of inertia about this axis, we can say Iy will be 1 by 12 ml square. That we determined in the last case for a rod of length L. The moment of inertia about the axis passing through its center, that was 1 by 12 ml square. So in this case, this length is perpendicular to it, breadth does not take any part in this case, and the moment of inertia will be same as moment of inertia of length L. So here the moment of inertia about the y-axis is 1 by 12 ml square. When we take the axis passing through the center and perpendicular to the breadth, then the moment of inertia we can write the moment of inertia about this axis is Ix. Then moment of inertia about this axis, which is perpendicular to the breadth, is 1 by 12 mb square. 1 by 12 mb square. So these are the two axes about which moment of inertia we find out 1 by 12 mb square for this axis perpendicular to the breadth, and the moment of inertia about this axis perpendicular to the length is 1 by 12 ml square. When we take third axis, which is perpendicular to the both of the axis, then the moment of inertia about this axis will be we use here the perpendicular axis theorem. According to perpendicular axis theorem, the moment of inertia perpendicular axis to the two perpendicular axes is equal to sum of moment of inertia about two axes. So that will be Ix plus Iy. So here Ix is 1 by 12 mb square plus Iy is 1 by 12 ml square. We take the m and 1 by 12 common, then we get m square plus L square. So this is the moment of inertia for a plate or a rod of rectangular cross-sectional area about an axis passing through its center and perpendicular to the cross-sectional area. Like this axis, this is the plate and this is the axis about which we determine the moment of inertia, which is 1 by 12 mb square plus 1 by 12 mb square plus L square. But this is the rectangular plate of rectangular cross-sectional area. But if we have a plate of square cross-sectional area, we can say length is small a and breadth is small a. Then moment of inertia about the axis perpendicular to it. Like this board is the plane of this plate, and this marker is the perpendicular axis, and passing through its center we can derive this axis by this symbol, the circle and dot in that circle. So moment of inertia about this axis will be, from this formula, 1 by 12 m breadth square plus length square. So breadth is small a square plus length is small a square. So moment of inertia for a square plate about an axis passing through its center and perpendicular to the plane is I equals to here 1 by 6 m a square. 1 by 6 m a square. So here today we discuss two cases. In first case, we determine the moment of inertia for a rectangular cross-section area or a rectangular plate, and in second case we determine the moment of inertia for a square plate, which is 1 by 6 ma square, and for the rectangular plate 1 by 12 mb square plus L square. We can remember this formula, and from this formula we can derive this formula. We don't need to remember it, but if you remember, it will help you to become faster. And from these two formulas we can derive the moment of inertia about different axes. Suppose that this, you know the moment of inertia about this axis, you know the moment of inertia about this axis, and the axis perpendicular to the plate. But if suppose you need to determine the moment of inertia about this axis, if you are asked to determine the moment of inertia about this axis, then you can use here the perpendicular axis theorem, parallel axis theorem, and here the parallel axis about to it, and the distance between two parallel axes is L by 2. So you can use it, the parallel axis theorem. And if you need to determine the moment of inertia about the axis passing through center of one edge and perpendicular to the plane, like according to the marker, then you can determine the moment of inertia from the parallel axis theorem. And when you use the parallel axis theorem, the second parallel axis will be here. Here are two parallel axes, and the moment of distance between two parallel axes is L by 2. And here, if you determine the moment of inertia about this axis and you use the parallel axis theorem, then the distance between two parallel axes is B by 2. So you can use any parallel axis theorem, and you can determine the moment of inertia about any axis. Suppose that you need to determine the moment of inertia here, then you need to determine the distance between two parallel axes. You have a parallel axis here and you have this parallel axis, and the distance between this distance is L by 2, this distance is B by 2, and this axis will be the root of L by 2 square plus B by 2 square. So if you have two parallel, you know the moment of inertia about the center, and you can determine the moment of inertia about any axis perpendicular to the plane, just determining the distance between two parallel axes. So here we complete the moment of inertia about a rod or a rectangular cross-sectional area and a plate. In next video we will determine the moment of inertia for a solid sphere, after that hollow sphere and a cylinder. So these cases are left. We completed here today. Please make the notes, revise it, and solve all the examples and numericals from your textbook. And best of luck.